In this video, we're going to review a technique from Calculus 1. It's a technique for finding antiderivatives, and it's called substitution. Substitution basically amounts to reversing the chain rule. Rather than trying to explain substitution in the abstract, I'm just going to do an example of it. So this is a pretty typical example, and one reason it's very typical is we see the expression x cubed plus 5, and we also see, at least up to a constant multiple, we see its derivative. The derivative of x cubed plus 5 is 3x squared. And so that reminds us an awful lot of that x squared that's there. So what we're going to do is we're going to make the substitution u equals x cubed plus 5. And then we compute what we call the differential, du, and that's equal to 3x squared times dx. And it's probably pretty likely that you've not thought about what a differential is in a while. For right now, the best thing that you can think of is it's formally as though you computed the derivative du dx, which is 3x squared, and then you multiplied both sides by dx. That's not actually really what it is, but it's a good way to kind of remember what this differential, how you write this differential. So having done that, we're going to rewrite this antiderivative in the form antiderivative of square root of x cubed plus 5 times x squared dx. And the reason we're doing that is because x squared dx is something that shows up in this formula we have over on the left side. So in fact, the way we can make this even more precise is we can multiply both sides by 1/3, and you get that 1/3 times du is equal to x squared times dx. And so now this x squared dx that's up here, we're going to express it as 1/3 times du. Having that idea coming up then allows us to say this whole integral in terms of the language of u. So this is now the square root of u, and then instead of x squared dx, it's 1/3 times du. And we'll write this as 1/3 times the antiderivative of, let's call it square root of u, actually let's call it u to the 1/2 times du. And so at this point, you should almost imagine that you've never even seen the letter x before. The independent variable is named u, and I'm going to write this a little more neatly. So this is u to the 1/2. So now what's the antiderivative of that? U is our independent variable at this point, so it becomes 1/3 times, this is going to be u to the 3/2, and then we divide by our new exponent of 3/2. Don't forget the plus a constant. Of course, this is dividing by 3/2 is the same as multiplying by 2/3. So this becomes 2/9 times u to the 3/2 plus c. And at this point, we're going to actually write the letter u in terms of what it originally was, which is x cubed plus 5. So this is 2/9 times x cubed plus 5 to the 3/2 power plus c. And that's our first review example of how substitution works. Here's our next example. When you first look at this, it might be tempting to try something like u equals 5x. That's actually a pretty good idea, and in fact, that's a legitimate way to do this. You could do that and then do another substitution on top of it. I'm going to take a slightly different approach and do kind of everything at once. Also, you might consider trying u equals cosine of 5x. You might consider trying u equals sine of 5x. That's what I'm actually going to do, is u equals the sine of 5x. And at the end, you can kind of think about why it was actually better to do the sine of 5x rather than the cosine of 5x. So if you do that, the thing you always do immediately after that is compute the differential, which is cosine of 5x. and then you have to multiply by the derivative of the inside, that's the chain rule, times dx. So again, it's as though we computed du dx and then multiplied both sides by dx. The reason this is a good substitution to make is because we can rewrite our integral now as sine to the 7th power of 5x, so it's really sine of x raised to the 7th power, times cosine of 5x dx. So this last part right here, cosine of 5x, that's identical to what we see over there. So we can now write this as, let's take our differential and multiply both sides by 1/5. 1/5 times du is equal to cosine of 5x dx. And that allows us then to take our integral and express everything in terms of u. So this thing is going to be 1/5 times du, that's going to be up there. And now we have u to the 7th power, that's the sine of 5x raised to the 7th power, times 1/5 du. And what is this? Then this is equal to, well, let's factor out the 1/5 and get u to the 7th du. And at this point, I'm going to write it as 1/5 times u to the 8th over 8 plus a constant. And this now becomes u to the 8th divided by 40. So let's actually call this sine of 5x raised to the 8th power divided by 40 plus a constant. So that is our final answer here. And again, it's kind of a key step here is when you got to this point where you had this integral expressed in terms of u, you can act like you've never heard of the letter x before, treat u as the independent variable. This is our last review example of substitution. It's a pretty tricky one. If you've done substitution for a while, you might kind of get in the habit of saying, well, I'm going to take the thing that's underneath the radical and call that u. So it seems reasonable to say u equals x squared plus 1. And without thinking ahead, I'm just going to plunge ahead and say the differential of u is 2x dx. That might look problematic because you kind of wish that it was something like 2x cubed dx, and it's not that. But there's a way we can kind of get bailed out here. What we can do is we can rewrite this integral by sticking one of the factors of x at the end and leaving two of the factors of x in front of the square root. So in other words, we have x squared, square root of x squared plus 1, and then we've got x dx at the very end. And this x dx certainly reminds us a lot of what we have over there. So it seems at least like a good idea for now to say 1/2 times du is x times dx. So that's what we have over there. And you might look at this and say, well, fine, but I don't know what to do with that x squared. Well, we're going to deal with that in a kind of clever way. So we're going to leave some space where this x squared is. And then I'm going to write square root of, and instead of x squared plus 1, I'm just going to put a u in there. And then instead of x dx, I'm going to put 1/2 times du. And of course, what's at the beginning? Well, what's at the beginning, I still need to deal with this x squared. And at first, it looks like we don't have a way to deal with that. But if you take this original substitution that we made, you can write it as x squared equals u minus 1. In other words, you can write x squared in terms of u. And that means that this x squared up here is really just u minus 1. So I'm going to take my substituted integral and write a u minus 1 right there. So now we've expressed the entire integral in terms of the variable u. It still might look hard, but it's not as hard as it might seem. We're going to factor that 1/2 out, and then we're going to distribute actually the other direction, we're going to distribute the square root of u through those parentheses. So we get 1/2. And then when we distribute the square root of u through there, we get u to the first power times u to the 1/2. That's u to the 3/2. And then minus u to the 1/2. And then we still have this du sitting here. And at this point, we're in pretty good shape because that 1/2 can sit out in front. And this u to the 3/2 can become u to the 5/2. That's 3/2 plus 2/2. And then we have to divide by 5/2. So that's the same as multiplying by 2/5. And then the next term, u to the 1/2 is going to become u to the 3/2. And then we have to divide by 3/2. That's the same as multiplying by 2/3. And then we have a plus a constant. And that's basically the final answer, except that we need to express everything in terms of x. So I'm going to do this in a different color. It's going to be hard to fit here. We're going to have 1/5. That comes from combining those two things. So 1/5 times x squared plus 1 to the power 5/2. And then we're going to have minus, and then we have to combine the 1/2 and the 2/3. So that's going to be 1/3 times x squared plus 1 raised to the 3/2. Okay, and then last but not least, we need our plus a constant. So this thing right here, that's the final answer for this guy. And again, this was a tricky problem. The hard part about it is that we kind of had to split this x cubed into two pieces. One of the pieces could be kind of captured by the differential. The other piece, you had to kind of take that substitution and write x squared in terms of u. So that's it.